Hello everyone, so I'm Ralph Potter at Codeplay. I work on bringing machine learning to heterogeneous processors using SYCL. So we're really interested in how do we get from these high-level programming models like Python, so here we've got some TensorFlow code, down to hardware, so whether that's FPGAs, whether that's GPUs, DSPs or what have you. So I'm going to cover some of the challenges of accelerating machine learning on heterogeneous hardware. I'm going to talk a bit about OpenCL and SYCL and our work to bring OpenCL support to TensorFlow. And this is primarily a talk about engineering and not so much a talk about machine learning theory. So machine learning today is being used to solve a wide range of problems that are challenging or impossible to solve with just conventional imperative programming. So it performs really well at something like vision processing, where it might be really hard to hand code a whole series of features to detect whatever we regard as the particular properties of a cat or a dog or what have you. Lots of machine learning algorithms are really computationally intensive, so that makes putting them on GPUs or other accelerators really attractive. But at the same time, there's a wide variety of hardware out there that people want to target with machine learning, whether it's supercomputers all the way down to smartphones, DSPs, really tiny devices and also really large power-hungry devices. And with so many devices to target, getting this done in a productive way without producing hundreds of implementations is a challenging problem. So machine learning is a field that's evolving really rapidly. We see new papers every day, new operators, new neural network layers. We also see new hardware appearing incredibly quickly. And so we need some kind of stability. If we're developing new operators and new algorithms, we need to be able to put them on something without also chasing new hardware at the same time. So we need a programming model that gives us a point of stability in the middle. So today there's already a plethora of machine learning frameworks out there targeted at data and domain scientists, whether it's TensorFlow or Caffe or PyTorch. And the users of these frameworks are not typically systems programmers, they're not typically parallel programmers, and they're not typically interested in dealing with the nitty-gritty of how do I make something fast on a GPU, how do I make something fast on a DSP or an FPGA. They're building models as computational graphs, and they want that to be accelerated on whatever hardware they have. So these frameworks have high-level interfaces, typically Python, but internally they're typically implemented in languages like C++. There's a lot of CUDA for GPU compute. And these frameworks are often large. TensorFlow is somewhere in the region of 700 plus operators. So if we were to look at TensorFlow on CUDA today to give us an idea of the architecture, users are coding against Python or against C++. That's what they're writing their applications in. This is all going through a static C API that exists for TensorFlow. And then inside TensorFlow itself, we find a whole series of kernels, specialized matrix multiply and convolution operators that are either built on the eigenlinear algebra library for the majority of operators, or are going back to NVIDIA's CUDNN for hand-coded optimizations. Which, this is fine if what you want to do is target an NVIDIA device. They've shipped a great kind of software stack there. But what happens if we want to target something else? Well, we lose CUDNN. We lose eigen unless we find some way to compile the C++. And so we have this gap between the C API and whatever our specialized hardware is. So to move on to OpenCL, OpenCL gives us a parallel programming model that can address a wide range of hardware. And it gives us functional portability across these devices. I can write my kernels on, test them on one device, put them on another device, and I know that they will execute. It doesn't guarantee us performance portability, which we'll come back to later, but we can guarantee that functionally we can transfer it. And that gives us some degree of stability against changes in the hardware underneath our code. So moving on from OpenCL, we have SYCL, which is a higher level specification built on top of OpenCL. So this is a specification expressed in C++ that allows us to write all of our code in a single source file, interleaving both our accelerated code that we might put on a GPU or a DSP and our host code to control it. The SYCL framework will manage our data movement for us. And it also, by virtue of being C++, brings us template metaprogramming and allows us to do things like template specialization to deal with those cases where the performance might not be portable. We can always extract the small kernel of code that is not necessarily portable from a GPU to a CPU and specialize just that and leave the rest of the surrounding code intact. Also, SYCL is based on offline compilation, unlike OpenCL. That allows us to do all sorts of strong type checking between our host code that we're going to compile down to the host processor and the code that we're going to run on the device. So by virtue of SYCL building on top of OpenCL, that means we can execute it on a huge range of platforms, whether that's CPUs or GPUs, accelerators, FPGAs, DSPs. So as far as SYCL is concerned, we expect end users to write applications. Maybe they target SYCL directly, but more likely perhaps they just use a C++ template library that builds upon SYCL. SYCL in turn builds upon OpenCL, and that allows us to target this wide range of devices while still allowing users to just use a familiar template library or to write their own code just against SYCL's interfaces. In terms of machine learning, if we look at the same diagram, we've got data and domain scientists working in Python, targeting TensorFlow, which replaces our template library in the previous diagram. And that's just building from SYCL down to OpenCL, down to the accelerators that we mentioned before.
Hi everyone, my name is Thomas Kim. Today is November 20th, 2020. This is my 10th episode about linear algebra, GPU, OpenCL, SYCL, TBB, oneAPI, DPC++, Compute C++, C++ AMP, Heterogeneous computing, data parallel algorithm. The reason I read all the words in this long title of the playlist is that everything in this title is important. In this episode, I will discuss how to run all CPU cores and all GPU processors all simultaneously. I highly recommend you to watch machine learning using heterogeneous C++ and SYCL this video. I also recommend you to watch other videos in this list. I assume you have watched my previous video listed here. If you haven't watched my previous videos, in this playlist, linear algebra, GPU, OpenCL, etc., it might be difficult for you to follow my current and future sessions. Without further ado, let's get started. Start Visual Studio Code. Open your working folder. I will create an empty folder 010. The title is CPU, GPU, all. Click this button, CPU, GPU.cpp. Hit enter, Ctrl B. I warn you in advance that this session can be a bit challenging for most of you, but Keep this in mind that once you know it, everything looks a simple piece of cake. If this video is challenging to you, that means you have to watch more of my previous videos about C++ programming, include CL, SYCL HPP, include talk play fun, output HPP, talk play fun, stream, auto, and talk play fun, and auto, and L, talk play fun, and L. For the review what we've learned in the previous episode. Into main, copy the function name, copy, paste it here. Start your command prompt, cd 010 CPU, GPU, all, clang ++, SYCL, C++17, CPU, GPU.cpp, o c.exe, hit enter. Copy the command string, copy, paste it here. Now dp cpp ehsc std c++17 CPU GPU.cpp o m.exe, hit enter. I will copy the command string, copy, paste it here. Here, SYCL CL int size 10. Instead of this, copy, paste it here using SYCL int. Then copy this, paste it. SYCL Q we use default device selected by the implementation or DP C++ compiler. I will scroll up. SYCL buffer type is CL int 1. Buffer size. This represents type that the buffer will hold. 1 is rank, one-dimensional array. Buffer is one-dimensional array that can hold size element, 10 element. SYCL range 1, one-dimensional range. We provide buffer get count. We initialize range to buffer count element or size elements. Sorry, this is constructor, so we have to remove semicolon. Auto action, we capture as reference this buffer. Also capture range. Then SYCL handler. Don't forget semicolon here. Auto accessor buffer get access SYCL access mode read write. Don't forget we have to pass handler. This handler comes from lambda parameter. This handler. Auto kernel we capture accessor by value. SYCL ID 1 IDX. Don't forget semicolon. Accessor IDX. Please note that this IDX is type SYCL ID. Don't worry about this. I will explain it shortly. IDX get. We have to provide dimension. 0 means the first dimension. If you have experience in Intel TVB, this range and this ID must look very familiar. Here, handler parallel for class, dummy class, we pass range, we pass kernel. Now here we use this queue and submit this action here. Our device runs independently of the host CPU or accessor. We use buffer get access SYCL access mode read. We do not provide anything. Please compare. In this case, we provided a handler. In this case, we provide nothing. For int I less than size plus I stream I accessor I. If you have watched my previous video, you should be able to understand what we are doing. I introduced the concept of range for the first time. By passing range, this range is decrypted, then passed to this argument as IDX to kernel lambda closure. It returns size t, so this accessor actually accesses the elements of buffer. Its type is SYCL int, so I do typecast. Now we build again. We will use clang compiler CLSC. We created buffer 10 elements. Using kernel, we initialized like this. First off, I hate this long enumeration. I copied, scroll up, and paste it here. I will fix like this. Context pair, auto, SYCL, read, write. Copy once again, paste, paste. This is read, this is write. I fixed like this. Also using dummy type void. Now scroll down. I hated this, so dummy type. Also SYCL read. Also SYCL read. I fixed like this. It becomes much shorter. See this part? I defined void. Let's try it with the clang compiler. Voila, it works. Using dpcpp, hit enter. It also works perfectly. Now I will refresh it. Scroll down. I will fold up and disable it. Void test CPU, GPU working together. Copy, paste. Int size 1,000,000. SYCL Q CPU SYCL CPU selector. Copy, paste. GPU selector. We learned about GPU selector and CPU selector in our previous episode. Now SYCL buffer CL int 1 buffer. This is array. Please note that buffer is an instance of a SYCL buffer that can hold type int one-dimensional buffer arrays. I will copy this, copy, paste, size t, size, copy, paste. So we initialized buffer with 2 elements. 1 buffer, 2 buffers. Now here, SYCL range 1 range. I would say buffers, ranges. Don't forget semicolon. We copy this, copy, paste, buffer 0 get count. Copy, paste, buffer 1. So we created 2 ranges. Auto action selector. We capture buffer. We capture ranges. It should be buffers. Int selector. Don't forget semicolon. Return. We capture buffers, ranges, selector, SYCL handler, auto accessor, buffers, selector, get access, SYCL write. We have to provide handler, auto kernel. We capture accessor, SYCL ID 1 IDX semicolon accessor IDX. I don't think we need typecast here. IDX get 0. Now here I will create a block Q CPU submit. We call this, we select 0. Please note that we call this lambda and the pass 0. 0 represents CPU. Q GPU submit action selector 1. At this point, all CPU cores are busy. All GPU PEs processing elements are busy. Auto accessor 0, buffers 0, get access, SYCL read. Wait until buffers 0 is released by the CPUs. Or accessor 1 buffers 1 get access SYCL read. Wait until buffers 1 is released by the GPU's PEs. Or sum up buffers ranges SYCL handler semicolon or accessor 0 buffers 0 get access SYCL read handler or accessor 1 buffers 1 get access SYCL read write handler or kernel accessor 0 accessor 1 or IDX semicolon accessor 1 IDX equal accessor 0 IDX. We forgot one thing. Handler parallel for dummy type ranges 0. Kernel scroll up. I made a mistake here. Before we return handler parallel for dummy type ranges selector kernel. I forgot this part. Scroll down here. Q GPU submit. This action sum up. We recycled Q GPU to sum up buffers 0 and buffers 1. I say add up buffer 0 and buffer 1 element wise. Or accessor buffers 1 get host access for int I less than size plus I. Stream I accessor I and there. Now scroll up. We'll make it 10. After testing, we will modify this size. I understand it might be a little bit challenging, but if you watched my previous videos carefully, there should be no problem understanding this code. Especially this part can be a little bit challenging. In the lambda, we return another lambda. We pass the selector as lambda capture. Then we can use this selector to select the buffer and ranges. In this lambda closure, if selector is 0, then buffers 0 is selected. If selector is 0, buffer 0 is selected. This buffer 0 is fast to kernel either GPU or CPU through accessor. Then we initialize accessor. If select is 0, then buffer 0 is initialized. If selector is 1, then buffer 1 is selected, the buffer 1 is passed to the kernel and initialized. So in this case, we are initializing buffer 0 using CPU cores all in parallel. In this case, GPU, we pass 1 to this lambda closer, then select becomes 1, buffers 1 is passed to the GPU kernel and initialized. All cores of CPU, all processors of GPU are executed simultaneously at this point. Now scroll down. In this case, we pass buffers. Buffer 0 is accessor 0, buffer 1 is accessor 2. In case of buffer 0, this is read. In case of buffer 1, this is read-write. Because accessor 1, we add up with accessor 0 element-wise. This sum up operation is executed by GPU. I made mistake here. It should be IDX. And it should be 1. Now we build CLS using Clang compiler. We have definition with the same mangled name as another definition. It is associated with kernel. So I will copy this error, copy, control home, paste it here. Now scroll down here, template, auto, index, 0, and struct I modified like this. Dummy type is now struct, but does not have a body, does not have definition body. Now scroll down. I will unfold, scroll down. I fix like this because index 0 is default. Now I will fold up, scroll down, here, 1. This type is dummy for name mangling kernel. Kernel is lambda. This dummy type is used for name mangling kernel, this class. This lambda closure is a class internally. Scroll down. Here, I pass 2. This is a type. This type is used for name mangling kernel C error definition with the same mangled name. So this type is used for name mangling. Now we build again. CLS C. We created 2 queues. One is queue CPU, one is queue GPU. We initialized CPU selector for queue CPU. We initialized queue GPU with GPU selector. So queue CPU runs using CPU cores. Queue GPU runs using GPU processors. Here we created 2 buffers, buffer 1, buffer 2. Each buffer has the same element size. We resolved size elements, but we haven't initialized the element value. Here we created 2 ranges, one range, another range. If we scroll down, we created action selector. This action selector returns lambda closure. We submit this action selector with 0, 1. It itself returns this lambda closure. When selector is 0, we initialize buffers 0. We initialize buffers 0 using CPU. When selector is 1, we initialize buffer 1 using GPU simultaneously. Then, these are for synchronization purpose. There are more efficient ways, but this code is good enough for demonstration purpose. Now, here, buffers 0 is the first buffer we initialized using CPU cores. Buffers 1 we initialized using GPU processors. Here we add up buffer 0 with buffer 1 element-wise using GPU because we used Q GPU. We submitted this action. Now here we wait until buffers 1 is released by the GPU's PEs. Then we print out the result. Of course, we could make this into array 2. Also, if we have multiple GPUs, for example, AMD GPU, NVIDIA GPU, or multiple graphic cards are installed on your machine, then we can create multiple queues for each device, for each graphic device. Then we can use full computing resources of a computer all in parallel. This code might look complex, but once you learn C++ language correctly, this is just piece of cake.